scales. Now again, to recap, log means the power. So if I have 2 raised to the power of 3 is 8. This 2 is called the base. This 3 is called the power. And 8 is the result. This is called the exponent form or the index form. Exponent form. How do you convert this into a log form? I mean, it's worth writing down, important. You say log, the word log, you have the base coming at the bottom, then you have the result sitting along, equals to the power. Now if I have to transpose this one into log form, I say the word log, the base is 2, the result is 8, and the power is 3. So that means 2 raised to the power of 3 gives me 8. Alright? So that's the very, very basics of log. Now, let's talk about what are log scales. So I'll just take this off the board slightly. Am I okay to take this off the board?
Yeah.
Now, let us say you have the weight, you are drawing basically a graph between x and y where, let us say, your x values are very, very small to very, very large. So I have 0.1, I have 1.0, then I'm just making something up, 100, and I have 1000. Right? Let's say these are my x values, and my y values are any values, 5, 8, 10, 12, 15. No, there's nothing. And this is, let's say, 10,000. Now the problem comes, why we are using log scales is, when you draw the graph, y is very simple, you can scale, right? You can say, okay, I'll start from 0 here, and then cool, this is 2, 4, 6, 8, 10, 12, 15, easy. Problem is scaling the x. How will you scale x? Scale of x is what? It is very, very low and very, very high. So it is practically impossible for me to scale here. I mean, I can't say, alright, this is 0.1, then obviously if this is 0.1, your 1, which is like 10x, should come here, sorry, 1. And then your 100 would probably come here. And so you cannot scale. The problem is scaling the x-axis with so much variation in the data, in your x. So what we do is, we convert this x into logs. So I say, let's convert it into logs. And one more thing which I forgot. When I use the word only log, so for example, I say log 100. What will be the answer? You can ask me, there is no base. When there is no base, it means the base is 10. You should know this. In mathematics, they don't write the base of 10. They just write log. So when they say log 100, you should know what power should I give to 10 to give 100. So answer should be 2. Got it?
Yeah.
Tell me one thing, Smara. If I say log base 10, 0.1, what will be the answer? Negative 1. Very good. Why? 10 raised to the power of minus 1 actually means 1 over 10, which means 0.1. Okay? So log answers can be negative and log answers can be positive. Now let's convert this x into log values. What will be log of 0.1? We just calculated as negative 1. What will be the log of 1? Tell me, what will be the log of 1? If I say log base 10, 1 is equal to how much? Good, 0. Why? Because 10 raised to the power 0 is 1. Right? Anything, any number in the universe, when it's raised to the power of 0, answer is 1. This is 0. What about here? This becomes 2. This becomes 3 and this becomes 4. Now, you see, if you forget this for a second, you see now it is very scalable. Right? So you can start from here. You can say, okay, I said this is my negative 1, that's my 0, that's my 1, that's my 2, that's my 3, and that's my 4. Finish. And here you say, I'm scaling log x. So, you have converted a regular data into log data. This is why the log scales are used. If you have very high and very low numbers all together in your data set, you can compress them to become more realistic to scale them down. Any problems here? All good? All right. And in your CAS, you can go and find the log. Easy, you can find the log of any number in your CAS, right?
So you know how there's like different ways to do it. So I meant like as in like questions like.
So this is the log weight. If this is the log value, if you have to convert the log value back to the original value, look here, you just need this power to sit on 10. So if I have to get a negative, an actual number from this log number, I'll say 10 raised to the power of negative 1. See, answer will be 0.1. You get this back. If I have a 0 and I want to get it back, my original number, I say 10 raised to the power of 0 equals to 1. For that matter, let's say if there was a number which was 5.2 and I need the real number back, I will say 10 raised to the power of 5.2, and you can only do it in your CAS to get the answer. This is how, so I taught you how you convert the actual number into the log number and how the log number can be converted back into the actual number. Is this clear? Yes? Good. Shall we do maybe one more question?
Yeah.
So we're going to talk about correlation. And causality. Correlation means you have an EV and you have an RV, two variables, and we draw the scatter plot and we say, all right, they are correlated. This is like a strong linear positive correlation. Simple, right? That's what we need. That's what we know so far. Causality means, as you said rightly, cause and effect. Something caused and had an effect. So, for example, height and weight. Height increased, weight increased. Height decreased, weight decreased. So they have a proper causality between them, a cause and effect. And obviously correlation is anyway there. If you see the scatter plot, we can clearly see it's a linear positive correlation. So not only the height and weight have correlation in terms of the scatter plot, in theory, practically speaking, logically speaking, they have causality as well. They are interrelated. Now, if I ask you an example where I say, if I draw a scatter plot between the number of sunscreen used on a day and number of people fainting on that day, and if I draw that scatter plot, I will get this kind of a scatter plot. It tells me that this is a strong correlation. That means more number of people applying sunscreen, more number of people are fainting on that day. Less number of sunscreen applying on that day, less number of people are fainting. Do you think that makes sense?
Yeah.
Why?
Because the more, because it's going up, it's increasing.
No, I'm not talking about the correlation. Correlation makes sense. But generally, if you think logically, forget about this.
Yeah, it doesn't make sense.
More sunscreens applied on a day, that means more people fainting. Has application of sunscreen has anything to do with number of people fainting on that day? No. But the problem is when you draw the scatter plot, you see it's a perfectly positive linear correlation. But causality does not make sense. There is no cause or effect. Logically speaking, this is irrelevant. Right? Now, think about this one. You have, let's say, temperature on a day. If the temperature on the day is high, do you think people will faint more?
Yeah.
If the temperature on that day is high, do you think the number of sunscreens applied will be more?
Yeah.
So what is happening here? Behind the scene, there is something which is impacting both of them. So there is a hidden factor. There is a hidden factor which is, not a hidden factor. So there is a common factor which is driving both of them. And if we forget this and we draw the scatter plot between the two, I get a perfectly positive correlation. So this kind of a scenario where you have something behind the scenes common to both EV and RV, driving them up or down, creating a positive or a negative correlation, I call this kind of a scenario as the common response scenario. Note it down. In the question given in the exam, if you get something like this where you find there is something common at the background which is driving the two, but then they are not related to each other at all, there is no relation between them as such, I call this scenario as common response scenario. Is this clear? Right? Now let's take another one. Shall I take this off?
Yeah.
Let's take another scenario.
So, like, how are you supposed to know? Like, how is the question gonna be worded to ask you?
Let's see. I mean, you will find an on off questions. I mean, we'll see if we can get something here, right? Let me just explain it and I'll just, make more sense. Now, another scenario is I'm just taking the example from the book, they're very, very cool, wonderfully explained. The unemployment in a particular country and the crime rate in that country. Do you think they are related?
Yeah.
It's absolutely. More the unemployment, more the crime. Less the unemployment, less the crime. So they're perfectly correlated. Great. But there could be another scenario behind the scene. There could be another variable sitting behind the scene which is impacting both of them as well. What is that? Let's say you have to think about it. The economy of that country. If the economy of the country goes up, unemployment goes down, and hence crime goes down. If the economy of the country goes down, the unemployment goes up, and hence the crime goes up. So economy can directly be associated with unemployment, and economy can directly be associated with crime. So if this is your EV and this is your RV, if I forget this, there is a perfect correlation between EV and RV. Along with that, you have another variable, another reason which might be impacting both of them as well. So in this case was economy. So you call this scenario as confounding variables. Confounding means hidden. Confounding variable. So what is the difference between confounding variable and common response? In both the scenarios, we had something in the background related to EV and RV. But in the common response, there was no correlation between EV and RV directly. You said there is no relation between sunscreen and fainting. Whereas here, the unemployment and crime had a direct relationship between them. And they had another variable sitting in the back, just like the common response. Does that make sense, right? So, this scenario is called confounding variables. In both the cases, the linear plots, the scatter plots will be perfectly linear. They could be positive, negative. I mean, if you just see the scatter plot, that makes sense. But behind the scene, there's another story going on impacting both of them, which is driving the causality. This variable at the back is the causality, is doing the cause and hence the effect. Make sense?
Yeah.
Yes? Sort of? Fully? Yeah?
Yeah, I understand it.
And the last one is coincidence. I'll just take this off the board. Coincidence. Coincidence. Let's say, Samara, if I make a scatter plot, and this is funny, number of people having butter in their breakfast versus the number of divorce rates between couples. And if you see, you will see a linear scatter plot, which actually tells you more the number of people are eating butter, more divorces are happening. Do you think this makes sense? This is absolutely rubbish, right? So, and you cannot find a common reason behind that as well. So this scenario where there is no confounding variable, there is no common response, and it's absolutely weird, I call this as coincidence scenario. Make sense? Now, we go to data transformation. So far what we've done was we have analyzed the data. Now we are going to transform the data. Transform means change. So far what we've seen is that our scatter plots were like this. Perfectly linear. Right? Or positive linear, negative linear. What about if my data starts to deviate from not being linear to becoming non-linear? So let's say my data becomes, rather than this, starts to go like this. So that means the data becomes non-linear. When the data becomes non-linear, we have to transform the data. We have to transform the data to make it linear. Okay? How do we make it linear? We can transform the data in three ways. Number one is called square transformation. Number two is called log transformation, and whatever we've learned about log will come in handy. Log transformation. And number three is the reciprocal transformation. Okay? Now, when you have, let's talk about just the transformation. Let's say you have this data set here, which is non-linear. So this data set needs to be converted into a linear form. I have to somehow make this line bend like this, so that it becomes, rather than a curve, it becomes a straight line, right? How do I bend it, Samira? If I start pushing this dot forward, and then do you think if I connect these dots, this line becomes straight, right or wrong? So when I have pushed these dots, stretched these dots forward, what have I done? I have increased the x values, right or wrong? Because I've horizontally moved it. So this data, so if I take the example of this data, the original value was here. If I pulled it, so now the new value is this. So I have just pushed it on the x. What about this data? You see here, the original value was this. That's the new value. You see, I have pushed it too long. So what am I doing? I am increasing the x values to make this curved line look straight. Let's take another example, Smile. Let's take this example. Let's say my data is this. That's my scatter plot. How does the scatter plot looks like? A non-linear scatter plot, right? how can I make it look linear? If I just push this up, straighten it a bit, it can be linear. So if I pull this line, this dot here, 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 and this dot here, and I then draw the line, it becomes a linear scatter plot. Are you getting it?
Yeah.
What have I done now?
Increase the RV.
Exactly, I love the word RV. Thank you for using it. People call it Y. I love RV. RV, you increase the RV, the Y value. The Y value. So, you increase the Y values or the RV values. Right? When you increase your EV or the X, or when you increase your EV or RV or the Y, one way to increase the values is square transformation.
So increase both of them?
Just one at a time, depending upon how your curve is. If your, and that's a good question, if your curve is something like this, Samira, you increase X. And if your curve is something like this, Samira, then you increase your Y. Depending upon how your curve is. And how do you increase it? First way to increase it, or the only way to increase, not the only, probably the best way to increase it, square that value. And how do you square that value? For example, if I take somewhere down here, let's say your X and Y, your EV and RV. Let's say this was 2, 4, 6, and you had like 10, 20, 30. How do you increase the X? What you do is you square them. You say X square. 2 becomes 4. 4 becomes 16. 6 becomes 36. And now you forget this in the middle. And now you create a scatter plot between the increased X value and the Y value, and you get a linear scatter plot. Did you get it?
Yeah.
So what you will do eventually in your CAS is, you will be given the original X and Y, and you might be given a scatter plot which is non-linear, and you'll be asked to say, apply an appropriate transformation to make this plot linear. So what you need to do is, you look at the shape of that scatter plot, the non-linear, and if it is one of these two, and you have different shapes for the other transformation we'll take in the next lesson. If you see, okay, this is this kind of curve, increase X. This should go into your bound reference. So, okay, so then what you do is, increasing scatter, increasing X means squaring. Square all the X values in your spreadsheet, and now create the scatter plot with X square and Y, rather than X and Y. Now your X square becomes your EV, and Y remains the RV. And then you make the scatter plot, you'll see the scatter plot becomes.
Can I write this down?
Sure. That is what square transformation is all about, and we'll deal with log and reciprocal